Hello, everyone. Welcome back to this online class. Today, we are going to look at the Fourier Sine Transform as used in solving partial differential equations. In particular, we are asked to solve the boundary and initial value problem defined by our PDE is the one-dimensional wave equation, which is valid from 0 less than x less than infinity and t greater than 0. The boundary conditions at x is equals to 0, our solution is 0. And we are also told that the solution vanish and also the first derivative of u with respect to x vanish as x approaches infinity. That's at the other end. The initial condition at t is equals to 0, the solution is 0. And again, at t is equals to 0, the derivative of u with respect to t is also 0 for all x greater than 0. So we need to use Fourier Sine Transform. But you see, at some point, you might not be even told which transform to use between Fourier Sine and Fourier Cosine Transform. So what will guide you is the boundary condition at the starting point, at the lower end. That is what will guide you to know which transform you are supposed to use. If the boundary condition at the lower end, if you know the solution at the lower end, then use Fourier Sine Transform. But suppose you are told this one, take note, you look at boundary conditions at the lower end. The lower end, for this case, it is at x is equals to 0. So if you are told u over 0t, if this is given, then it means you use the Fourier Sine Transform. But if you are given u subscript x at x is equals to 0 t, now look at, if you are given this boundary condition, then you use the Fourier Cosine Transform. So that is what will guide you between choosing between the two transforms. Now, for our question, look at the boundary condition that you are given at the lower end. It is simply u of x, u of 0t. So I'm going to go for the Fourier Sine Transform. Even if you are not told which one to use, this is what will guide you on which transform to use. Now, having explained this one, let's now go back to our question and solve it. Of course, the steps are as usual. You need to find, first of all, we are going to say let f subscript s denote the Fourier Sine Transform operator. It's operating in the variable x. Now, somebody might ask, what is the difference between Fourier Sine, Fourier Cosine Transform, and the Fourier Transform, the complete Fourier Transform? The difference here is that in Fourier Sine and Cosine Transform, our domain is semi-infinite. When you have a semi-infinite domain, just like this one, from 0 to positive infinity, then you need to use either Fourier Sine or Fourier Cosine Transform. And I've told you the choice, what will guide you on which transform to use. So, and when you have a complete domain from negative infinity to positive infinity, in that case, you cannot use Fourier Sine or Fourier Cosine Transform. There, you're going to use the complete Fourier Transform, the usual Fourier Transform, where you need to integrate from negative infinity to positive infinity. So you need to take note that when we talk of Fourier transform, the domain extends from negative infinity is from negative infinity less than x less than positive infinity. When you have such kind of a domain, you use Fourier, the complete Fourier transform. We'll have written here complete or complex Fourier transform. But when we talk of Fourier sine transform or Fourier cosine transform, the domain is semi-infinite, is from 0 less than x less than positive infinity. So this one is semi-infinite. This one is infinite. So when you have an infinite domain, use the complex Fourier transform. When you have a semi-infinite domain, use either Fourier cosine transform, so this Fourier sine transform, or Fourier cosine transform. So that's the difference between those three transforms. And the difference between the Fourier sine transform and the Fourier cosine transform is you look at the boundary condition at the lower end. When you see the solution at the lower end as given, then use Fourier sine transform. But if the velocity at the lower end is given, velocity means we are differentiating now, then you use the Fourier cosine transform. So I having explained those critical information, let us now go back to our question and solve it. So here, we have f subscript s as our operator. That is the Fourier sine transform operator. It will operate on the variable x. So now, the first step, we write here step 1. What do? We operate with f subscript s on both sides of the PDE. So that will give us the Fourier sine transform of second derivative of u with respect to t twice is equals to Fourier sine transform of c squared second derivative of u with respect to x twice. Remember, c squared, that's just a constant which can be factored out. So when you take the transform, this is what we need to get. On the left-hand side, that will now be ODE, d squared dt squared of the Fourier sine transform of u of x t. That's how it will be transformed. On the right-hand side, I will have c squared times the Fourier transform of second derivative of u with respect to x twice. And that Fourier transform, of course, we are not going to derive it because I expect that you know how to derive that Fourier transform based on the given boundary condition. So this is what you're going to get as the Fourier transform of the second derivative of u with respect to x twice. It will give you omega times u x0, u0x, u0t, I mean, u0t, then minus omega squared times the Fourier sine transform of u of x t. That's what you need to get. Somebody might be wondering why we are getting this from. This is the definition of the Fourier sine transform, that the Fourier sine transform of any function, let's call it u of xt, is equals to the integral from 0 to infinity. Now here we will have sine omega x times u of xt dx. So that's how we define the Fourier transform of any given, the Fourier sine transform, I mean, of any given function. So when you use that, you're going to get what we have found here. Of course, you're going to use integration by parts, but I believe you already know how to derive such kind of a transform. So having known that one, let's now apply the boundary condition we are given. So the second step, step 2, you now apply the boundary condition at the lower end. The lower end, that is when x is 0. So we are given that u of 0t is equals to, that is supposed to be equal to 0. So what do we remain with? Was it 0 or 1? Just a minute, I check. The boundary condition at the lower end for this equation, this problem, it was 1. I had written 0 by mistake. This solution, this condition is given as 1. Let's have it as 1. So let's apply that. Where there is u of 0t, you need to write 1. So it means this value here is 1. So 1 times omega, that will just be omega. So what will be our equation? So therefore the ODE will now be d squared dt squared of the Fourier sine transform of u of xt is equals to c squared into omega minus omega squared Fourier sine transform of u of xt. That's what we have. You can also rearrange it. You can also rearrange this so that you can write or d squared dt squared of the Fourier sine transform of u of xt. Then now I want to take this to the left-hand side, so it will become plus c squared omega squared times the Fourier sine transform of u of xt. And now on the right-hand side, we now have c squared omega. So I can use a d operator. So you can say let d be derivative with respect to t. So this will imply that if I want d squared, that will now be the second derivative with respect to t twice. Remember, this is an ODE. So therefore, this one is an ODE of second order with the constant coefficient. So our ODE will now look like this. In terms of the d operator, it will now be d squared plus c squared omega squared times the Fourier sine transform of u of xt. Of course, not time, but it should operate because an operator is operating on a function. So that d squared plus c squared omega squared is operating on the Fourier transform, Fourier sine transform of u of xt to give us c squared omega. This equation is homogeneous. I said it is ODE, second order, non-homogeneous with constant coefficients. It is also linear. Linear second order ODE, non-homogeneous with constant coefficients. So how do we solve this kind of equation? There are two types of solutions. The first one is the complementary function. Another one is the particular integral. So let's start by finding the complementary function. Complementary function, this means I'm going to solve the homogeneous part, that is d squared plus c squared omega squared, operating on the Fourier Sine Transform. Now I'm going to call this function uc of xt. Uc to mean, okay, let me not write because that will confuse us a lot. Let me write u of xt is equals to 0. So what is the auxiliary equation? Auxiliary equation, that is d squared plus c squared omega squared is equals to 0, so that the roots here, we have two roots, that is d1 and 2. d1 and 2 is the square root of negative c squared omega squared. And you know, square root of a negative number is a complex number, so this will be plus or minus iota times c omega. So these roots are complex conjugates. Complex conjugates. Complex conjugate roots. So therefore, your solution, therefore, our complementary function is equals to, call it C1 cos C omega. There's a T, cos C omega T plus C2 sine C omega T, where C1 and C2 are arbitrary constants. So that is complementary function. Let's find the particular integral. Particular integral, you need to make that Fourier Sine Transform the subject of the formula. Remember, this is what you are solving. This one. So particular integral, it is equals to 1 over d squared plus c squared omega squared, operating on c squared omega. So that is what we have. So how do we find it? That's the question. You see, c squared omega is a constant, is a polynomial of degree 0. It's a polynomial of degree 0. Polynomial of degree 0. It is a constant. So then it means you are going to drop the powers of d, or those terms of d with higher powers than the degree of the polynomial. I'm going to drop d squared because d squared 2 is greater than 0. So you drop it, so that what you remain with is 1 over c squared omega squared, then times c squared omega. And so this will give you, because I can see the c squared will cancel, and even the omega will cancel with 1 of the omega. So we just have 1 over omega as our particular integral. So therefore, Our general solution is the sum of those two solutions, complementary function and particular integral. So the general solution is given by the Fourier Sine Transform of, or let me write this, general solution is simply equal to complementary function plus the particular integral. Or what we write to the Fourier Sine Transform of u of xt is equals to, the other one we got C1 cosine of C omega t plus C2 sine of C omega t plus 1 over omega. That's what we have. Now, we have initial conditions that we need to apply. So that's the third step. You can write step 3, apply the initial conditions. So you write step 3. Here we now apply the initial conditions. So what is the first one? We are told ux0 is equals to 0. So the first condition is that u of x0 is equals to 0. So because look at our general solution, it is in terms of the Fourier Sine Transform. So before I apply the initial condition, u x0 is equals to 0, I must also know the transform of that initial condition. So this means that Fourier Sine Transform of u of x0 will also be equal to the Fourier Sine Transform of 0. And that will give you 0. So that means on the left-hand side, I'll write 0. And when I put t is equals to 0 on the right-hand side. So therefore, you can just say that therefore, 0 on the left-hand side, we are substituting here. We are putting t is equals to 0 in that equation to get the solution to be 0. So 0 is equals to, and remember cosine of 0 is 1 and sine of 0 is 0. So this is the same as C1 cosine of 0 plus C2 sine of 0 plus 1 over omega. So just like I've said that sine of 0 is 0, so this term will vanish, and cosine of 0 here is 1. So we only have C2 times 1. This is 1. So this implies that 0 is equals to C1. The C2 is not there because that is times 0, so then plus 1 over omega. So, or C1 is equal to negative 1 over omega. So that's the value of C1, negative 1 over omega. So let's replace it back. So hence, you can just say hence, if I replace C1 by negative 1 over omega, what are we going to get? We are going to get Fourier Sine Transform of u of xt is equals to negative 1 over omega. Then here we have cosine of c omega t plus I don't know C2, then sine C omega t plus 1 over omega. There's another initial condition to be applied, the derivative of u with respect to t. So let me differentiate this. So we are going to differentiate with respect to t on both sides. So what are you going to get? When you differentiate, you're going to get Fourier Sine Transform of u subscript t of xt. I've differentiated it with respect to t. What about the right-hand side? Derivative, of course, is negative sign. So this should be equal to negative, of course, negative sign will cancel with the other negative, so that what we'll have is just positive c omega over omega. So positive c omega over omega, then sine c omega t. The other one, differentiate sign, you get cosine. So we have c2 times c omega cos c omega t, and the other one is a constant, which when you differentiate, you get 0. So, which I don't even need to write. And you see here, I can see omega will cancel with this other omega. So you can write this as c sine c omega t plus c2 times c omega cos c omega t. That's what we have. On the left-hand side, you can just write Fourier Sine Transform of u subscript t of xt is equals to that. So now we need to apply this condition. Apply u subscript t of x0 is equals to 0. So from here, what does it mean? That if I take the transform on both sides, I'm going to get Fourier Sine Transform of u subscript t of x0 should be equal to the Fourier Sine Transform of 0, which is equals to 0. So that means that in this equation, the one that I am bracketing, if I substitute t is equals to 0, I need to get that transform to be 0 on the left-hand side. So therefore, upon substitution, we are going to get, you can just say therefore, 0 is equals to c times sine 0, because t is 0, c times sine 0, plus c2 times c omega times cosine of 0. And you know, sine 0 is 0, so I don't expect this. This will be 0. And the cosine of 0 is 1. So this is 1. So what do we have? Is that 0 on the left-hand side is equals to C2 times C omega. When I divide by C omega, I'm going to get C2 is equals to 0. Because the C is not equal to 0, omega is also not equal to 0. So it is C2 that is equals to 0. So remember, C is not equal to 0. Omega is not equal to 0. So C2 must be equal to 0. So therefore, we come back and replace it here. We can just now say that hence, the Fourier Sine Transform of u of xt should now be equal to, I've replaced C2 to be 0, so I'm just going to get -1 over omega cosine of c omega t. The other one is 0, so we'll have plus 1 over omega. And how else can you write this? You see, 1 over omega is common. So this can be written as, you can just say, or the Fourier sine transform of u of xt is equals to 1 minus cosine of c omega t, everything you divide by omega. So that is what you're getting. And you can simplify this further. Remember that 1 minus cos 2 theta, I want us to take note. Take note here that when we talk of sine squared theta, sine squared theta is usually equal to 1 over 2 into 1 minus cosine of 2 theta. There's a closing bracket before this one, so I need to close this. But I don't need to express that in terms of sine squared because it will make our work difficult when integrating. But I just wanted to bring to your attention that identity which you can use when there's a need. Now, the last step, step 4. Is now operate with f subscript s inverse. That means the inverse Fourier sine transform. You operate with it on both sides of this equation. The one that I have bracketed, this one, we can call it star star. I hope we have star somewhere. So operate with f s inverse on both sides of equation star star. So when you operate on the left hand side, you are going to get u of xt. Remember, f inverse and f, of course, fs inverse and f subscript s are inverses, and so when you operate on them, you get the identity operator. And identity operator operating on any function gives you the same function. So on the left, you'll have u of xt is equals to, on the right, we'll have f subscript s inverse of 1 minus cosine of c omega t, everything over omega. I want us to recall the definition of the inverse Fourier sine transform of any given function. Let's take note. When we talk of f subscript s inverse of any function of omega, call it u capital of omega t. It is defined by 2 over pi times the integral from 0 to infinity of the function you're getting its inverse, that is u of omega t, that's the function you're getting its inverse, times sine omega x d omega. That is what we call the inverse Fourier sine transform. Inverse Fourier sine transform of the function u of omega t. Now we want to follow the same idea to now find the inverse Fourier Sine transform of what we have there. And remember, when you find the inverse, you will go back to a function of x and t. That's very important, where x extends from 0 to infinity. So therefore, this one can now be written as, this one you can now write as 2 over pi, the integral from 0 to infinity of 1 minus cosine of c omega t over omega. This you multiply by sine omega x d omega. And if you know, you see, you can be able to work out this kind of integral, but you can as well leave your answer in this form. But this integral can be simplified. So what we have there is what we are calling the solution corresponding to the given boundary and initial value problem. If you have time, you can be able to apply the techniques of integration to work out this kind of integral. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems on Fourier sine and Fourier cosine transforms. Bye-bye.